Good evening, everybody. Good evening, and welcome to BrisScience. It is October 2024. I am your MC for this evening, Joel Gilmore. I am so excited to be here tonight at BrisScience, our series of free public lectures on science held once a month at the fabulous The Edge at the State Library of Queensland and presented by the University of Queensland and their long-term support for this fantastic series. We'd like to start by acknowledging the traditional owners of the lands on which we're meeting tonight and pay our respects to elders past and present. And very relevant to our topic this evening, we acknowledge that the actions we take as we live and work on these lands do impact on these lands and waterways that the First Nations people of Australia have had a deep connection to for over 50,000 years. And we seek to tread lightly in everything we do. So if this is your first BrisScience, thank you so much for coming out. This is one of our lecture series where we aim to bring not just the best scientists, but also fantastic communicators to share their research with the audience of Brisbane. And of course, all our talks are live streamed and recorded and will be up on YouTube next week, so you can catch up any of those details you missed, as well as look at all of our past talks. There's a lot on there now. We would like to invite you, of course, to take your phone and put it on silent at this point. You might even want to check that your phone is indeed on silent at this point. And while you've got your phone out, checking if your phone is on silent, this is a great opportunity to note that at the end of the talk, there will be an opportunity to ask questions of our speaker. And we will do that through a Q&A app. So you can scan this beautifully timed QR code. Congrats to the IT team there. And, oh, it's gone again. You can scan the QR, we'll put it up at the end as well. And we will take as many of those questions as we can at the end. And afterwards, we'll be having some food and drink just out the side there. So we'd love you to hang around and chat to both our wonderful scientists and also yourselves about what we discussed tonight. All right, without further ado, tonight we are getting down and dirty to talk about dirt, or more specifically, soil and soil health, and how our agricultural systems are holding up as we humans continue to pollute as we are known to do. Our speaker tonight is Dr Nicole Robinson, who is a researcher in the Plant Nutrition and Ecophysiology Research Group at the University of Queensland. Nicole has over 2 decades of experience in thinking about how plants and microbes and fertilisers and soil all interact in our cropping systems. We are very excited to have you here tonight, and so to kick off some fertile discussion about fertile soil, please welcome Dr Nicole Robinson.
Oh, thanks everyone. I'm very glad to be here this evening to share some of our ideas about how we can develop sustainable agricultural systems with you. But I'll admit right now that we don't really have all the answers, but hopefully by the end of the evening, we'll be able to look at some of the directions that we should be heading in. So the first question is, though, what are sustainable agricultural systems? And I think Joel gave it away a little bit, and hopefully you can get a hint from the other picture that I have on the slide there of a tractor with a fertiliser bin. So my particular area of interest is soil fertility, with particular emphasis on nitrogen. So first of all, if we introduce the topic, having a look at what's happened with nitrogen fertiliser over the years. So here we've got a graph illustrating the increasing world population over time, but also if you have a look at the little purple squares, hopefully there you can see that one. You can see after the 1960s, there was a very rapid increase in fertiliser consumption, and also associated with this, also an increase in the total anthropogenic reactive nitrogen. And what this is the amount that is available for our plant growth. So the fertiliser increased over time. We did have increasing yields during this time, but it's not directly related. So there is a decrease in efficiency, so the amount of crops that are produced for the amount of nitrogen that's gone in, and this is leaving it very vulnerable for losses. So that's where we really want to target in increasing this efficiency. So if we have a look at what is the result of these increased losses and this increased reactive nitrogen, you can see here this image that's shown was first come up in about 2009, where there was ideas that were raised looking at exceeding the safe planetary boundaries. And really this was one of the first times that nitrogen, from our point of view, came into the global spotlight, where you can see, if you have a look in the green section, this is considered the safe operating space. But if we have a look here, the amount of nitrogen, the different fluxes of nitrogen, and the amount of reactive nitrogen was well exceeding that space. And even with the updates of this particular planetary boundaries, considering the risks and the uncertainties, nitrogen has really remained exceeding and a real problem in terms of global biogeochemical cycles and the impacts it has. And that's also alongside, you can see climate change and biodiversity. So often those ones are very often in the spotlight, but not always this nitrogen cycle, and thinking about nitrogen transformations, fertilisers, and how it moves from the farm into the food we eat and then into the wastes that we excrete. So that's thinking about it on a global level. What I wanted to do today is give you a snapshot of a more local example here in Queensland, looking at Queensland sugarcane cropping, because that's an area in which we've worked in for a really long time and has a lot of relevance to everyone here tonight, I'm sure. But to tick off the stats of what we're talking about when we're talking about sugarcane cropping, there's about 31 million tonnes of sugarcane that's harvested annually across 355,000 hectares of Queensland and some of northern New South Wales, worth $3.8 billion, so quite a large economic significance for the state, and about 20,000 jobs, with this stretching to about maybe 4,000 farms or businesses. So what's the link with nitrogen? So you might have been aware, because there was a lot of action and activity talking about the impacts of sugarcane cropping on water quality within Queensland, particularly by the state and federal government over the last few years. Here we've got the picture showing a satellite image, because a lot of sugarcane cropping is located on the Queensland coast in very close proximity to the Great Barrier Reef. You can see with the large rain events or with a lot of water moving out from the catchments, here you can see the sediment, but associated with that is also the dissolved inorganic nitrogen that hasn't been taken up by the crop and is leaching out into the Great Barrier Reef Lagoon, which has quite a high load of dissolved inorganic nitrogen as compared to previously before this cultivation was occurring. And that's provided food sources for crown of thorn starfish larvae, sort of escalating that predator of the reef, also adding to the impacts of climate change on reef health, and also general eutrophication, which you can see here in the diagram at the bottom. So as well as these water quality impacts, we also have to consider another aspect of nitrogen losses, which is greenhouse gas emissions from sugarcane cropping. So the agricultural sector does contribute about 20% of these greenhouse gas emissions, but also in particular, sugarcane cropping is very vulnerable to losses of nitrous oxide, which is a potent greenhouse gas as well. This is because of the high nitrogen inputs that occur in very wet environments. So you think about the Queensland coast, very heavy rainfall events, also often a lot of irrigation in those systems. And so you can see from this graph here, we've illustrated the season. Once the fertiliser goes on, this is when the crop is really small. It doesn't have much capacity to take up the nitrogen, and so it's there very vulnerable for loss. There's a lot of inorganic or nitrogen available in the soil, and this has potential to be converted into the nitrous oxide. So you can see those peaks there that are well removed from when the crop is taking up the nitrogen. Sugarcane has quite a long crop cycle, almost 12 months, in some cases up to 2 years. And so the nitrogen uptake occurs for quite a long period of time, and maybe is quite separate from when the nitrogen is getting onto the field. So there has been a lot of action with trying to amend and reduce these dissolved inorganic nitrogens that is going on to the Great Barrier Reef, and there has been a lot of changes to nitrogen fertiliser regulations, but you can see here as the latest report card that we've had with this trying to reach these targets of 60% reduction in the nitrogen that's leaking onto the reef, and that 60% target was hoped to be reached by next year. But you can see here for the latest release report card, we've got very poor marks in terms of water quality, despite all the activities, with an E. Oops. You can see here, so it's quite an E. We're not quite at even halfway point for the target for next year, so showing that there is a lot more action, or we do have to take a lot more transformative changes in our nitrogen management other than just reducing the fertiliser rates. And so that's what I'm hoping to talk to you about this evening. So how can science, and how have we been trying to help with this issue? And here I've got a bit of a toolbox, or some of the approaches that we've used over the years or investigated in terms of how can we tackle nitrogen losses, how can we improve these nitrogen use efficiencies, particularly for sugarcane systems, and how that's characterised in this tropical crop. But this is also relevant to many other agricultural systems, particularly horticultural crops and others where there might be higher nitrogen applications and challenging managements. So what are the toolboxes that we have? And here I've listed it in order of how we've progressed with approaching this throughout my career. So when I started, I was very plant focused, wanting to understand how plants worked, not necessarily only for agricultural species, but for how all plants used nitrogen, stored nitrogen. Over the years, this has broadened out, and with working in agriculture, I've realised the importance of soil and soil microbes, and how this is all interacting together, and most recently, how we can use the knowledge of understanding all these different components with how we can best formulate fertiliser, or how we can maintain soil fertility, or add nutrients to the crops. So here, if we take a step back and have a look at the comparisons of what we might expect for two different systems, with clearing of the land and replacement of forest systems, which is quite a tight nitrogen cycle that is very circular, and this has a lot of recycling of nitrogen in the system, compared to a sugarcane field where you have large applications, or relatively large applications of fertiliser at particular times. So here it's a bit of a simplified nitrogen diagram. So what we have is a large bank of soil organic nitrogen. With agriculture, some of this is disrupted, and those transformations are maybe increased, and it starts cycling through from proteins to amino acids into those dissolved inorganic nitrogen I mentioned earlier, which is the ammonium and the nitrate. And it's particularly the nitrate that's very mobile and very vulnerable to loss through leaching, or also in transformations through to nitrous oxide and the greenhouse gases. So the first thing that we tried to do was look at the nitrogen use efficiency of different plant varieties. Because often when we're dealing with crops, the first, one of the main approaches is breeding, and how can we make varieties that are better at either yield or, in this case, nitrogen use or nitrogen uptake, so they can maybe grow a lot more with less nitrogen, or they're very responsive to nitrogen. When we first started this work resource use efficiency was not really what hadn't been selected for within the Australian germplasm of sugarcane development. And so we were really interested in looking at what was the range that was available and how we could maybe improve on having a lot more yield with much less nitrogen in the crop. And we did this by using a sort of on-ground harvesting, and here you can see is about 60 or so different varieties of sugarcane that are represented in the satellite image, where we grew them under very low compared to high or recommended rates of nitrogen fertiliser to see if we could identify particular varieties that did very well that we could maybe focus on to enhance this nitrogen use efficiency. So here, this square is representing like one crop of a different variety. But what we found was there wasn't a really large difference between those varieties that did well at low compared to high. So those, and following the breeding program, we were able to use those responsive varieties. So something that did well at high was also, in most cases, going to do quite well with reduced or sort of more moderate fertilisers as well. So this gave confidence that the breeding program wasn't really missing out on particular traits or others that were able to access nitrogen in a better way. So that was a good way forward, particularly where you just would find varieties that did very well under very, very low. But in those particular examples, this is not something that's very useful for crop production. But one thing that we did find was when we compared how the different plants use different forms of nitrogen, and in this case we compared how the sugarcane used the ammonium, which is the one form of nitrogen, as compared to the nitrate. So a bit comparing, like, do you like to get your protein maybe from soybeans, or do you like to get it from beef? In a slightly not that great analogy, but here I was looking at, because it's often thought that plants really favour nitrate as their prime nitrogen source, but we were interested in dissecting this in a bit more detail. And so what we did there was compare the commercial sugarcane variety with its parent type, so that's these two here, and then also some of the varieties that they were bringing in for other types of traits like drought resistance or other stress monitors. And what we found from this was that the commercial sugarcane variety was particularly poor at using nitrate as compared to ammonium when compared to even their parent species and also these other varieties. So this gave us the idea that we did have some opportunities to be able to enhance the use of nitrate by incorporating some traits from these other species. It also told us that we really needed to look at the nitrogen forms that were available in the soil. And even though the sort of main aim of everyone is to slow down the nitrification and production of nitrate a little bit to be able to prevent those losses, this was also particularly relevant for sugarcane as compared to other crops. Because when we compared it, then we thought, oh, we'll make a much broader suite and comparison of these different grasses and cereals. So there we also brought in comparing maize and sorghum to other sort of high-yielding grass species. And when comparing these, we found as well that they had a much greater capacity to store the nitrate as a form in their tissues and their stems as compared to this commercial sugarcane. So sugarcane really was not great at taking up nitrate compared to other species, and also didn't store it so well in the tissues. So this was also giving us another lead that could be investigated as to where we could tweak the varieties a little bit to enhance this uptake, and also focus in on looking at these soil transformations and really slowing down this production of nitrate to reduce the losses from sugarcane systems. So here we'll take a step back a little bit from here, because we've been talking about this in a broad cropping system. But here, when you look at it, it's really coming down to the soil, the root, soil and fertiliser interface. And this is really the key to crop nutrition. So here I was just talking a lot about the ammonium and the nitrate. Here we've got a picture of a root in the soil with around here in green, you can see the nitrate. There's water around it as well. So the plant is exuding some chemicals out of the root as well as taking in the nitrate and others. So it's accessing and trying to tease apart these particular mechanisms that will help us understand the different transformations at a root level, and then how these can be harnessed or manipulated to try and modify this soil environment to reduce these nitrogen losses. So that's the way forward in terms of looking at it from a plant point of view. I think the variety yield, the sugarcane varieties that we have are very good yielding, very responsive to nitrogen, but looking at how they can modify their soil environment is an area that is of a lot of interest. And there is other species such as sorghum and others that are able to exude these chemicals that slow down that transformation from ammonium to nitrate. So this is something as well that is worth investigating in more detail. So as well as the sort of crop impacts on this system and the nitrogen impact on the crop, there's also the soil biological community. So we're going to have a bit of a look at that in a bit more detail. So within the soil, those transformations from amino acids to ammonium to nitrate are facilitated by this microbial community, the different bacteria in the soil, the different fungus in the soil. But we really need to have a much broader approach to looking at this soil community other than just the bacteria and the fungi that are involved. So this is looking at the soil health, also the beneficial soil fauna and the other pathogens that might exist as well. So here we've got the system, again showing the plant with the root exudates and the impacts that has on the broader soil biology of the community. And one of the main goals of a lot of agricultural systems is to pick indicator species or highlight some changes that are occurring in these communities to give an indicator of crop health. And so that's another key target that we've had looking at this whole, how do we characterise this whole community that is filled with so many different organisms that are affected by so many different things, and how can we have a meaningful indicator to be able to tell growers and land managers what is the result of their management actions on this community. So we'll have a look at a couple of examples of this as well. So as I said before, the agricultural land use selects for these particular soil microbial communities, and they're very different to what we find under that native vegetation. What we have found when we compare those microbial populations in terms of biomass and also some composition is that it's been much lower under the sugarcane soils than it has under adjacent forest systems. And so we're hoping to try and tease apart and figure out why this might be the case. The general reasons are that when you have the plant litter going in, so in cropping systems, a lot of the green trash blanketing is cut off at harvest and returned to the soil. So there is plant litter going into the soil, but it's much more diverse than would occur in a forest system. There's also a lot of land managements involving tillage and other actions which disrupt the fungal networks and also the larger soil fauna. The fact that there's a lot of sugarcane for over many, many seasons also changes the soil community profile. So sugarcane is planted as a plant crop and then continues for many successive crops before it's removed, and can have a fallow or an intercrop that might disrupt or change the soil community. And then there's also the impact of mineral fertilisers, which is some of our particular interest. So there's a lot of action in looking at soil microbial communities, in particular their composition, and this has really occurred with the advances in different gene sequencing techniques, which really now can give a huge amount of information, but most importantly for a much less cost as well. So now there is a lot of work looking at characterising how these communities are changing with the changes in management. So with land use change, what's happening, and we were most interested in looking at what happens when you change the amount of fertiliser that's going into the system. So in this particular case, the rate of fertiliser being added. There's also changes that people look at with the different types of fertiliser. So different manures and other different types of amendments is a very interesting area of research also. But here our change was a bit more subtle than that. So we were trying to look at what happened when we had many years of just quite low fertiliser, around 20 or 40 kilos of nitrogen per hectare, as compared to the higher rates that were added. And here we had a look at this in the fungi and microbes that are associated very closely with the roots, so sampling the roots under these systems, and also with the bulk soil that was near it as well. And you can see here there is a bit of a change with the different composition of the larger groups of fungi. And when we dig into that in a bit more detail, and sorry for the big list here, but at the top we've got the list of fungi that were found under the low fertiliser treatment, and in red we've highlighted the pathogens. So before I said that there was a much smaller microbial community under the agricultural system than the forest, and we really probably want to have a healthy, large and dynamic soil microbial community, but it really is dependent what are the microbes that are present. So here we can see not that many are flagged as pathogens in the low fertiliser treatment, but then when we've got the comparative list below where we have 180 kilograms of nitrogen added, you can see there's a presence of a lot more pathogenic fungi coming into the system with the increased fertiliser rates. So this isn't a change of the type of fertiliser, just the amount that's being added. So a very low system as to a very high system, increasing the pathogens or the bad pest fungus. Similarly, when we compared this from the nematode population, so nematodes are often a key indicator species of soil health in sugarcane systems. They can cause a large impact in declining yield when there's the pathogenic nematodes present. And it's often looked at as an indicator of the health or the soil health of the system. And again, when we compared it under the low and the high nitrogen fertiliser, we found that the parasitic plant nematodes, so those that are causing damage to the crop, and bacterial feeding nematodes, where there's a high bacterial load, were really increased under these high nitrogen applications as compared to the beneficial predator nematodes, or those that were feeding on the other pest nematodes, were reduced and suppressed under the high nitrogen application. So just this increased amount of nitrogen being added to the system really suppressed the beneficial microbes that we had occurring there in terms of, the nematodes rather than the microbes in this system. So this is really indicating that as well as being a monoculture, which is often thought of as the key component driving the nematode communities, that the amount of fertiliser that was added was also driving the changes in this nematode system. So there are other components, and there's a lot of interacting factors that impact the soil health that need to be considered when we're looking for these indicator species and trying to help growers understand what really this is telling us. So that was sort of a quick dive into the soil biological community. The sugarcane industry has done a lot of work in trying to characterise soil health, and as well as select these suite of species or indicators that can be easily measured. But what to do with that information is really the key determinant of what needs to go forward. And what has been found is probably, instead of this sort of one-off comparisons, that there really needs to be a sustained monitoring system that goes on over a number of years, so that for particular sites, the indicators that are most important can be identified, and these would be monitored over time. So a really large, probably, investment and continued monitoring is really what's required to maximise the benefit from this soil health indicators or indicator species. Okay, so now coming up to the last one, nutrient formulation. So this is the area of work that we're probably most active in currently, and this is looking at the release of nutrients from these nutrient formulations is dependent on the soil and physical and chemical environment, and also the amount that are vulnerable to loss from the system are also dependent on the soil type that we're talking about as well. So in some cases, you can have some fertiliser going into the system and it is transformed into the soil and not necessarily vulnerable to loss in those systems. So the particular system and soil type is a key component of what is going to be the result of your nitrogen fertiliser. And also, of course, the water going in and the temperatures that are involved as well, driving these transformations of fertiliser. However, one of the big limitations of current mineral fertilisers in particular is that they're available as soon usually as they're added to the system, or very quickly after they're added to the system, and this is often very separate from when the crop needs it or they're going to take it up, because especially for sugarcane, we talked about earlier that the fertiliser goes on, it can be lost, but then the crop sort of grows after that. And until fairly recently, I would say there's probably been very little investment compared to the value of the fertiliser market into research and development. A lot of the developments and advances have been made probably by smaller companies. They're really interested in looking at different alternatives, and it's really not been until fairly recently, I would say, that there has been sort of increasing interest into investment into these the vast array of alternatives that can be looked at in terms of fertiliser technology. So what would they be? We would say these new fertilisers, one of the main aims is to have the nutrients, and in particular here I'm talking about nitrogen, become available when the crop needs it. So we're going to maximise the efficiency, maximise economic efficiency, and then it's going to just occur when the crop demands it. But you might be thinking, but actually I know there is a lot of these already available, and for some time there have been these enhanced efficiency fertilisers that do have delayed release, and these are often what you can see if you go to a hardware store or go to Bunnings. There's a huge array of different controlled release or delayed release fertilisers that are plastic coated, which slow the release over 3 to 6 months, so that is sort of matching more with the crop demand. However, there's still some limitations with these particular enhanced efficiency fertilisers. A lot of the coatings are done with plastics that aren't biodegradable and are adding to the intentionally added plastics to agricultural systems. So it has been found that these are very adverse effects on a lot of the soil fauna that we talked about earlier, in particular earthworms and others, where they ingest these microplastics and it really disrupts their functioning and that whole food web that we had a look at. And as a result of this, the EU is recently bringing in restrictions and regulations that are banning the use of these non-biodegradable coated fertilisers from next year that are intentionally added to the soil. So the idea of biodegradable plastics is a big one in sustainable agriculture, I would say, from the use of mulches and films and other, but often we don't think about it in terms of these tiny microplastics that are sort of being added as surface coating to the mineral fertilisers to resolve one issue, but maybe then adding much more to an emerging problem. So that brings us to our current work as well, which we've been doing alongside particularly Professor Bronwyn Laycock, who's the leader of the project within the School of Chemical Engineering. So together we've been working on looking at these novel fertiliser formulations where the chemical engineers are designing and manufacturing those, and we're coming up with the testing and evaluation of these particular products. There's a huge array of biopolymers that are available that can be used in fertiliser formulations. And here I've just got an example of one in the picture where it's a tiny pellet. So this one, if you have a look here, is around the same size as a fertiliser pellet that you would see that's generally, like if you're familiar with urea or other types of DAP fertilisers. But this one is not just coated with the polymer, it forms the matrix. So we've got a cartoon below there. And so you can see it becomes a matrix where the biopolymer is embedding the nutrient granules within it. So this may be a range of different fertilisers. In this case, we've used urea as a main fertiliser that is merged with different biopolymers. We also use different forms such as ammonium sulphate or others. And beyond that, globally, the work has been looking at having both nitrogen, phosphate and potassium all within sort of the NPK captured within these compound fertilisers. So here we've got the table of the different fertiliser formulations or the different biopolymers that we can choose from. This is a very limited table, and I'm not going to even attempt to try and pronounce the full names of those, but the acronyms we have here, the PBAT is one biopolymer. So we want to choose the biopolymers based on their different properties. Do they merge well with other nutrients? Are they brittle? Are they strong? Are they going to crush easily? They're the type of properties that we're looking at. But then the difficult thing in terms of nutrient release is having it but degrade or release the nutrient at the rate at which the plant needs it. So when you have the surface coating, sometimes you can have these burst reactions where that is fractured and all the nutrient is released. In this particular case, you can see you need the different pellet matrix to degrade over time to release those particular nutrients. So here we've got the PBAT, it's biodegradable but not renewable because it's sourced from petrochemical products. But then some of the examples that we've worked with, such as the PHA and PLA, are fermented waste like plant products, so plant starches or lipids, which could potentially be from waste streams that are then fermented with bacteria to produce these particular biopolymers. So they're both a biodegradable and a renewable resource that is able to be harnessed in these fertiliser formulations. However, the biodegradable part is the tricky part as well, is because at what temperature and at what rate are they going to biodegrade? Something like a film or a plastic, as long as it does the job and then as long as it's going to degrade over time, that's okay. But for fertilisers, we need this window that we want to have some certainty around in it being able to provide the nutrients for the crops. So that's where we came in. And so we've been screening these different combinations of the polymers with the nutrients under different scenarios. So the easiest and the quickest one is to immerse it in water over very quick periods of time. Here we can see at the top we've got just straight urea, so this is immediately available in the pink, and then moving through the different polymers, and then at the bottom, this one in the blue is Agromasa, which is a comparative commercial slow-release fertiliser. So you can see we've got a range of results that we have there over the 24-hour period. But then we move up into a more complex system, not as complex as the field, but here into leaching columns, so out of the full immersion into a sort of a flushed column. And you can see here it sort of changes the rankings. And we have the PHA is sort of shifting up where it is becoming more available as a result of some of this biodegradation that is occurring within that matrix. So this one is being flagged as something, you can see there, that's over a 60-day period of time, about 75% released of the total applied. So this is looking to be sort of a promising scenario for nutrient release with these bioplastics. Okay, so then though, what happens when we move to the field? You'll notice here that we've shifted away from sugarcane, which was the focus of the start of the talk, where we were looking at trying to find these solutions for tropical systems that were very much a bit more difficult to deal with than temperate ones. But this one we tried the field performance of the biopolymer in Toowoomba. This is based in just in a ryegrass pasture, where we had the capacity to do sort of a quick biomass harvest just with a lawnmower, as you can see in the schematic below, to try and gauge the growth and nutrient supply to the crop. And so over here we've got the biomass over time. This one here is in the different colours showing the different harvests with no fertiliser applied. Then we have the matrix fertiliser next to that at 3 different rates, so with increasing availability, and then compared to standard ammonium fertiliser. So in this case it was a PLA fertiliser, and you can see if you look at the green bars, it's pretty slow to get going because there is this delay in nutrient availability. But as you look at the second in the orange, this is where we really had a large release, or relatively large release of the fertiliser from the PLA, and it was able to get to similar levels of pasture growth as was found in the standard fertiliser. And then for the final harvest, with the changing environmental conditions, we didn't have much difference between the different rates or the different fertiliser types in this case. So this was promised, so there was sort of a delay being indicated, but then with an adequate release of the fertiliser in the second harvest. And we looked at characterising what was happening with the pellets over time by looking at them under a scanning electron microscope before they were used. So at the top, you can see there that that's the skin or the outside of the cylinder, and it's very smooth, not very many holes. Then down the bottom, this is the cut edge. You can see there are some holes there, but here this is evidence of the nutrient that's embedded in the polymer. And then after we retrieved them from the field, we saw that there were small holes in the skin around the outside, but most of the nutrient release was occurring from the cut edge, where the pits were becoming a lot larger, and then there's no ammonium to be found, and also there's a presence of bacteria and other microbes within those cut surface. So a lot of the nutrient is being released through the cut ends and through the different pores that are existing in this matrix. So understanding how the nutrient is diffusing and at what points really helps with developing further into the different matrices. Okay, so that's looking at the different biopolymers, and there's a huge array of those that are available with different properties that can be harnessed. But one thing that we haven't spoken about is also the potential for a lot of agricultural wastes, such as manures, mill mud, which is a byproduct of sugarcane milling, which contain a lot of the nutrients that haven't been used to be incorporated back into these fertiliser formulations. So as well as the mineral fertiliser, how this is then embedded into these different biopolymers that are available. We can also incorporate wastes as well as composts, and then use those with different combinations of sorbers, which help hold the nutrients together, and also with some of the biochar and other residues, increase the carbon into the soil as well, to start manipulating that soil biology and maintaining also the soil carbon-nitrogen ratios. With that as well, we've got the role of potential adding plant growth, promoting microbes, which is a huge industry or an area that is also being explored across different agricultural systems. So hopefully all of these will together be integrated by understanding how the plant is impacting the soil, how the plant's impacting the microbes, and how we're managing the soil through our inputs and management practices such as tilling will be able to increase soil fertility and reduce these nitrogen losses in sugarcane systems, but as well as that in much broader agricultural systems. Okay, and the last one, which I can't forget, is the grower innovation. So over time, we've had the great joy to work with a lot of growers who are really pushing ahead with being able to harness the innovation on their own properties by pushing forward with being able to recycle waste. And here's an example of Tony Rossi, who is a sugarcane farmer in Mulgrave region, who's really led the way in terms of optimising composting of different sugarcane waste products, and also optimising the placement of that within a sugarcane system, which, as I said, is quite difficult. It's a really large crop and goes over a number of seasons. And so they've really made a lot of gains with reducing fertiliser use on their property through this system. And so harnessing the technology and potential of the biopolymers with all these wastes and other sorbers is really, I think, where we really want to go in this field. And through that, with everyone more integrated together. So as a scientist, over time, I've really realised the benefit of integrating with industry and growers right from the outset. And so whereas before we would probably at the beginning only touch base with the industry right at the end of the project to tell them what we found, now we develop the projects with the industry and the growers to be able to really be able to produce solutions that are going to have real impact or be able to be translated into their farming practice. And that is the end. And of course, there's a huge array of people that we need to thank that have been associated with this work over the years. So there's a list of some there, as well as many, many others that are too numerous to name. So I'd like to thank you all as well for your attention, and I'll take some questions.
I might get you just Thank you so much. Very interesting talk, sparking lots of interesting questions about the future of farming. And there's already a bunch of questions coming in, but you can now add to that by scanning this QR code and putting your question into the Q&A chat. Now, little bits of housekeeping while you're doing that. I see you furiously typing away. Of course, this talk was being recorded and will go up on YouTube in the next sort of few days to a week, so make sure you log on there to check it out. If you are not already on our mailing lists and so forth, please sign up. Just search for us, BrisScience, head on to X, Facebook, and our UQ mailing list, and we will make sure you get all the information, which is very important because there is just one more talk left this year. That is next month. This is our BrisScience Science Spectacular end of year show, where we have a panel of 6 incredible scientists, communicators and journalists, including the amazing journalist Helena from Landline. You might have seen her if you watched that. She is making a guest appearance on our panel this year, so it's very exciting. It's a mix of games and comedy and a little bit of science education as well. I'm hosting it, so I'm very excited. So those tickets will be available online in the next week or so. It's just 3 weeks away, 4th of November, so keep an eye out for that. All right, are you ready for some questions?
Ready.
All right. First question we've got here. Let's go with Carly's question, who asks, do different crops require different timing of fertiliser release?
Yes, I think definitely different crops, but also the same crop in different seasons as well. So that's some of the difficulty is that often you can have the sugarcane might be in the ground for quite a long period of time, but until sort of the temperature is right and the water is right, then that's when you're going to have the increase. And also something like sorghum or a grain crop can be over much quicker, and so would need a quicker release as well. So that's the grasses and the grains. And then also with horticultural crops as well, again, where you've got production of vegetables or fruits, this also is going to influence it. So a leafy green needs the fertiliser very early and very quickly, whereas some of the longer ones, I would say probably sugarcane, maybe even tree species, much longer periods of time.
Brilliant. Nate asks, I've heard of potential GE, genetically engineered, I think, plants that can fix nitrogen from the atmosphere. Your thoughts on this?
Well, there's plants that have associations with bacteria and nodules, such as legumes, can fix the nitrogen from the atmosphere. So they have their own little fertiliser factory in the nodules. I think there might be some ideas of trying to incorporate this trait into other crop species. I would maybe suggest that integrating legumes into the system with other species like grasses or other might be another way to go, rather than trying to GM nodules into other, like those types of grains or rice or something.
Right. Shrek asks, I'm just reading them, nematode trapping fungi, tell me more.
Well, that would be something that's probably not my area of expertise, but there are fungi that grow within the soil that are parasitic and trap the nematodes and then can just like take the nutrients from there. So these are some of the maybe beneficial ones that we want to have enhanced if they're trapping the parasitic nematodes, but that's an area as well that I don't know a huge amount on. Yep.
Great. From Leah, who thought it would be a good idea to infect their soil with microplastics?
Well, many people. I think that maybe we've all, at some point in time, used some some fertiliser that's coated with polymers, like polyethylene that doesn't degrade. And so I think now we're really becoming aware of the impacts of even these small, like continual additions of these small amount of microplastics that are really going to have probably an ongoing problem. And it doesn't need to be, I mean, I think there's so many different alternatives that we can use and harness. So we just need to understand how to use them. So being able to use different polymers, understand their properties so they do adequate coating, how they're biodegrading as well. So biodegrading is good, it's what we want because we won't have a long-term impact, but then that would also change what we use these things for. So I mean, the plastics were brought in because they were sort of long-lived, could withstand some of these different changes. But yeah, I think it's something that the EU has said no more, and hopefully in Australia as well, hopefully that will also continue to have some follow-on effect. I think the industry is really taking notice. There's no use continuing to invest or roll out these ones that are also then going to be restricted. So it's really going to push development, I think.
Yeah. So Australia hasn't banned it yet, though?
Not that I'm aware.
Okay. From Casey, do sugarcane farmers not complete soil tests before fertilising each time? how can they use nitrogen fertiliser at the wrong time or when it's unnecessary?
There is a lot of soil testing, and a lot of growers do soil testing. There is now some regulations where in the plant crop they must do soil testing beforehand. The problem is, though, 100% of the fertiliser that is added is not taken up to the plant. So there is some balancing act that needs to be done between getting enough fertiliser on to be able to maintain yields as well and reduce losses. So that's where we would probably be, as well as reducing the rates, look at modifying the system so we have a different release or different regulation of these transformations within the soil to reduce the losses. And so there is soil testing and leaf testing. The problem is the unpredictable climate means that sometimes, and this particular type of climate that we experience in the tropics with very heavy rainfall periods that could result in a lot of leaching or runoff, creates this more potential for these lost pathways. So yes, there is testing, and mostly the regulation is, but matching exactly is the difficult problem.
Amazing. You up for a couple more?
Yep, sure.
Amazing. Okay, we've just got a couple more. So, well, actually, there's a whole lot more here, but we're going to ask a couple more. So there's a couple of questions about vertical farming, and also Seb says in parts of Spain there's a watering method that roughly translates to drip watering, where hoses drip water along the length of the crops. Could this be used to deliver a nitrogen-enriched water solution to avoid those large nitrogen dumps that might get washed away?
Yes, that is true. And there is some ideas in sugarcane system fertigation was trialled in some cases, but maintaining that system and being able to deliver it in that environment, in that soil, with the harvesting makes it problematic. So it's not able to really be maintained very easily. So if you think about a massive sugarcane field buried in soil, with small fertigation pipes, it has been tried, but it's not been really taken up because of these difficulties.
Okay. And there are sort of questions that touch on this idea that if fertiliser is such a big global industry, are the current producers, are they open to changes and new sources of fertiliser? Are there barriers? What are the practical challenges with this sort of...
I would say probably not as open as they should be, but I think if some of this if we have more governance, maybe in regulation, this will stimulate, because there's a lot of money to be made, I think, and this would open up maybe a lot more interest in this. But the efficiency and the ease of, I guess people continue with it because that's the way that it's easy. You can get a lot of nitrogen. If you've got your bag of urea, you have a lot of nitrogen coming in. We know how to put it on. You can predict it pretty well what's going to happen in terms of fertilise the crop. You can't always predict, we know what the loss pathways are going to be, but once we start tightening up that, that could create interest there. The difficulty with organics and others is that it's quite a variable, and what you get is sometimes getting that release that you can be certain of and being certain of adequate nutrient supply to the crop is a lot more difficult with organics, or where you have these different biopolymers where their release or transformation rates are impacted by a lot more other factors involved. And so I think farming is already quite an uncertain enterprise in most cases, and so another uncertainty like this means that I think a lot more support and extension is required for the risk to be removed and spread across all the different players in the field, including I would argue the fertiliser companies are part of that as well.
Yeah. So my very last question is, you're out in the field next week and you uncover a large crate of gold bullion, absolutely, definitely legal. What do you do next, related to science?
Oh yeah.
What would your project?
I think that what we really what we're hoping to do is come up with being able to test this integrated system. So as time's gone on, we've been very focused on different things like, can we tweak the crop here? How does this particular fertilizer or organic work here? What we really want to do is broaden it into an integrated system that has all these different components that we can work together with industry to try for a sustained period of time. I think it probably wouldn't be that unusual an answer for scientists to say we need longer to do things, but in terms of this cropping system, soil health, like 2 or 3 years doesn't really cut it. We need to continue things for long periods of time and build these knowledge bases. So that would be having a longer term projects that go over decades would probably be where I would be looking for.
Amazing. All right, well, we hope that it happens for you, but for now, could you please join me in thanking Dr Nicole Robinson for a fantastic presentation. Token appreciation, thank you. And we'll look forward to seeing you all next month. Now, please join us outside for some food and drinks.